Hi, I'm Soyeon, and I'm fortunate to be the last speaker of the lightning talk. I'm from UC Davis. Sorry. So I'm presenting my joint work with Tony Sharvin. She's my academic sister in UCSB. And I picked a different title for my lightning talk. But my current title in my lightning talk abstract is part of my long-term goal to understand the cohomology of varieties. So let me start by reviewing what was the author Richardson. So it appeared in Melissa's talk on Tuesday. She uses XUV circ notation, and Kristen uses RUV notation, but they are all equal. So they are an important object in the field of total positivity, causal algebra, and more. But today, what I want to assert is that they are also important in terms of cohomology. So their cohomology is appearing in many areas of mathematics, such as the fineness not invariant, called the Cohomology homology. Sorry. And QD number that George likes, Hilbert's scheme, Fermat module, and so on. So they're like kind of like scary objects. So you might wonder whether computing the cohomology of the super Richardson could be also like easy or hard. As you might expect, they are also hard to compute. So they are like not easily behaved. So they are smooth affine variety, but they are not compact and not closed. So they're open Algebraic affine variety. But there is one good thing. So as Christian and Melissa mentioned, Dr. Richardson variety has a cluster structure. So they are cluster varieties. And I am asserting that they are quite nice cluster varieties. Nice, I mean, is that they are locally discrete and really boring. But these are the technical definitions, so I won't define it. But you can ask me later. But anyway, they're quite nice, so you might wonder whether we can use the tools from the causal algebra to understand the cohomology of open Richardson, and that is what I'm going to do. But like partial cohomology. But anyway. So open Richardson varieties are nice causal varieties. Then Deweyne studied the affine smooth variety, and he observed that their cohomology are not totally random, but they are quite well behaved. So they are in the variation of the Hodge theory that you might expect, called the mixed Hodge structure. And Lemon Spire studied more on this nice cluster variety, and they figured out that their cohomology has this mixed Hodge structure, and but it is like even more than this. They are mixed tape. What this means is that, sorry. So if you want to compute the Kate cohomology group, we know that some part of the cohomology groups are vanishing. So we need to understand this like little smaller parts. We only know like partially about this cohomology. So if we know that K is equal to P, so if we have like H, K, 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 I wrote P, but anyway, K, K, K. But then these are called the standard part. And we kind of completely understand about the standard part. We know the Poincare polynomial, we also know the generators. But when this K and P are not equal, so they are called the non-standard part. Then we don't have much understanding because their cohomology are quite intricate. So we know that this K and P are 1 and 0 or 2 and 1. They are vanishing, so we don't need to care. It follows from the work of Lemon Spire or Brent. Yeah, I don't know where is Christian. Anyway, their work. Oh, okay, you're sorry. Yeah, but anyway, all from their work. And when K and P are 3 and 4 and 3, only partially known result is known by the work of same authors. So the partial result for the Poincare polynomial is known for the acyclic cube. And I highlighted this 4 and 3 because this is what I want to talk today. And also outside of this 4 and 3, we all know about the basis, not even for the Poincare. So I'm going to talk about the basis for this 4 and 3. So my keyword, so many people here define the keyword, so I don't need to define. So the keyword that I'm interested in is having this E-star keyword. So you have the center vertex V that is connected to like D vertex. If you see any of this like kind of keyword, any of this D-star figures in your keyword, then you're good to go. So if I am assuming that I could have some QI connected components that are also nice figure, that could be associated to this HW1, W2, W3, up to W3. And I can prove, we can prove the following thing. So for example, a trick keyword. For example, we know that their cohomology class for this 433 term is non-vanishing. And they are always D minus 1 choose 2. And moreover, when Q is a trig keyword, MSPy already computed their dimension for this Poincare polynomial in this case. But we can also describe a basis. I will give you an example. As an immediate corollary, people here care about the Dinkin diagram. So the cluster algebra associated to the Dinkin diagrams are called the finite types. And we can describe the basis for this Dn and E6, 7, and 8 were finite type cluster variety in all degrees using our basis. So I will talk about one example. So it could be having a many name. This is a D4 keyword, and I will call this 3-star keyword. So you have this 3 vertices surrounding your vertex that are going inside. So what would be the basis? So I am trying to label each vertices with something called the cluster variables, which are algebraically independent variables, the alpha, beta, gamma, and the top. And my bases are quite simple. So if we know the surrounding these vertices at each single source, and my basis in this case is 1 over delta times the wedge of the alpha, the beta, the gamma. So we can use this basis to describe the cohomology for the finite type for D and E. And I'm not talking about type A, we already know. Thank you so much.
Great question for Soyeon.
Oh yeah.
So is there a reason why people still for K equals K equals 1? Is there
Oh, like any other cases? We actually don't know. Outside of the foreign. Yes.
Is your theorem about the tree, is that just referring to the middle part being a tree? Or sorry, the theorem about the existence of a star? Is that bound? Does that include the frozen variables as part of the star, or is that?
Oh yeah. Oh, good question. So the tree, the keyword that I mentioned is like only about the middle part. Yeah. So if the middle part have, we can have this type keyword, then my theorem.
All right, let's save further questions for later, and thanks, Soyeon, I guess.